So the tutorial, the first one for today, will be on tractable probabilistic models, which is a very rich area within UAI. And as with any kind of area that sees a lot of excitement, you get this whole Sesame Street of acronyms that is being developed, the alphabet soup of models in AI. And so one of the goals for today will be for making sense of this whole alphabet soup. And these are all kind of models, AI representations that you may have heard of. And we'll very briefly touch on all of them. So there's a bunch of them that actually come from good old-fashioned AI, from logical AI, things like BDDs. And they're very closely related to tractable probabilistic models in ways we'll talk about later. But for now, we'll focus on models that are actually representing probability distributions. And so within those, you have your kind of classical probabilistic graphical models and other types of representations that unfortunately are intractable. And so most of this tutorial will be about how to build tractable probabilistic models, and we'll get into that later. And then among all the tractable models, the question is, if you want to be tractable, what's the price you pay? And then we'll talk about the expressive power of these models and whether you have to make any compromises. So that's kind of the high-level kind of takeaway. Let's make sense of this whole research field. So this is the outline, and we'll try to first motivate for you why we need tractable inference and the trade-off between expressiveness and tractability. And then we'll try to introduce some kind of common language for tractable circuits, which will cover a lot of the existing formalisms and try to make some kind of abstract general framework for talking about these things. So once we know the representation, we'll talk about how to get that representation, either from data or by compiling it from some other type of model that you like. And then at the end, we'll talk about applications and also conclude. So the first part will be why tractable inference, and so Antonio will present this part.
Thanks, Guy. Okay, before starting our journey into tractable inference, let's actually question why do we need probabilistic inference and probabilistic models to begin with. So suppose you are a decision maker, you are in charge to manage the traffic in Tel Aviv. So you may ask yourself, what is the probability that today is a Monday and there is a traffic jam on Herzl Street? Or maybe you are just a worker planning his own weekly routine. So you may wonder, which day is most likely to have a traffic jam on my route to work? So these are like basic questions we can formulate in natural language, and they are like queries. So how do you answer that? So suppose you have now data. What do? Well, of course, you're going to fit a predictive model. Let's say a classifier with a neural net. So you observe like questions and you try to predict answers. No. Because you're going to know in advance all possible questions, and you're going to need also answers, and you're never going to observe that. You're never going to do that. What we are going to do instead is to fit a probabilistic model of our world. This model is M, and we're going to query this model. This model is like a black box. We're going to make a question to this model, and these answers are what we call our way to do probabilistic inference. So I think we are in the UI community all on the same boat. On this. So let's have a quick look, deeper look into these kind of questions. So for the first one, what is the probability that today is a Monday and there is a traffic jam on Herzl Street? How are we going to answer this? So let's formalize this a bit. Let's say we have a bunch of random variables, x. We have time, we have day, and we have a bunch of Boolean variables indicating if there is a jam, a traffic jam on any of the streets there. So answering this query basically is computing the probability according to our model that today is Monday and this Boolean variable for jam on Herzl Street is true. We are ignoring all the rest. So basically we're doing marginals. We are marginalizing out all the other variables. Instead, for the second query, we have to do something more involved. So in the same formalism, in this toy example we're going to use throughout this first part, what we actually want to do is to compute the argmax of the probability according to our model M that the day is a specific day, and we have this logical constraint such that we disjoint all possible paths that are leading us to our route to work. So this is definitely more involved. It involves marginals, involves making like a map prediction, We're going to see in a bit what map means, and it goes making some logical reasoning about this. So far, it's like we're seeing two different queries, two different questions, and they do belong to different query families. So, since now we know that we really want to do probabilistic inference, let's try to be a little bit more formal and see what is tractable inference, what are these queries, and how do they relate to the model. So here's a simple definition. So we can say that a family of probabilistic models, capital M, is tractable for a class of queries Q, if and only if whichever M I pick and any Q query I pick from this family, I'm able to exactly compute the result, the answer for this query, given this model, in polynomial time, that is polynomial in the size of the query and in the size of the model. In practice, this polynomial time, as we will see, it's generally linear. So this is quite a good thing. But there is a caveat. So we also need to make sure that the size of the model and the size of the query are also polynomial in the size of the inputs. That is, the class of my models, my class of queries are compact representations. All in all, we really want to be able to answer these queries in polynomial time. So what about exact inference? Do we really know that? We can actually question if we really want approximate inference to begin with. Well, the question is, why would we want approximating things when we can go exactly to begin with? Of course, there is a price to pay, as Guy said, and we're going to see what it is later on. It's also good to remember that sometimes also approximations are not cheap. They are intractable. And most of the time, they also do not come with guarantees. There's going to be like a very nice talk by Rina talking about how to have guarantees in approximate inference routines. But generally, they do not. And whenever we chain approximations one another, let's say we are flying with a blindfold on. We do not know where we are going if we do not have guarantees. So this is a strong motivation to stick with exact inference. And this is like a violent fluorescent green to wake you up, to say that this is what I'm going to talk about in the next 15 minutes. So I'm going to introduce a bunch of these classes of queries, and at the same time, I'm going to review a bunch of families of models. And we're going to inquire, are those tractables? Are those expressive? What are we trading off? After this, we're going to introduce probabilistic circuits as a sort of grammar to produce tractable models. So let's start with a very basic probabilistic query we may want to ask. This is a question of this kind. What is the probability that today is a Monday, it is noon, and there is a traffic jam only in Herzog Street? Clearly, we need to instantiate all our variables. So basically, the day is Monday, the time is 12, and for all our Boolean variables, they all have a value. Everything is 0 except for the one for Herzog Street. This is complete evidence. It may seem a very trivial query. We might not really want to ask that to begin with, but if we really do probabilistic reasoning and learning, we have seen that quite a lot of the time whenever we do maximum likelihood learning, because we just want to maximize the likelihood of our data, which is generally complete. So this is our first kind of query, the simplest, I would say. Which kind of model, probabilistic model, are we going to use? Well, of course, we're going to use generative adversarial networks, which are super popular. Well, not really. To begin with, generative adversarial network not even have like an explicit likelihood. This is why you really need adversarial training. So people would say, yeah, but I can compute these complete evidence probabilities by sampling a lot. True, but you will need so many samples. And also, it's true that if you're doing adversarial learning, you're going to mod collapse sooner or later. So maybe you're not going to see many configurations, and your estimates will be quite biased. So we're not going to, let's rule out generative adversarial networks. And since we are not using generative adversarial networks nowadays, we must use variational autoencoders. And variational autoencoders now have an explicit likelihood, so we can compute this complete evidence. This is cool. So we're going to use variational autoencoders. Well, not really, because also in this case, we do have an explicit likelihood, but we cannot actually compute that exactly. So this is intractable because variational autoencoders are a mixture model with an infinite and uncountable number of components. So there is no tractable full complete evidence queries for that. And optimizing that is also problematic. So let's rule them out. Let's go back to, let's say, a more general family of models and to which variational autoencoders belong. Probabilistic graphical models. And PGMs are popular in the UAI community because they provide this very neat and clear separation between what's a model and how to perform inference on that. You know what a node is. It represents a random variable. You know what edges are. They do define the dependencies or independencies relationships among them. And you have a bunch of inference algorithms that act as a black box. So we really would like to use maybe a PGM, but we know there is some caveats. So let's review probabilistic graphical models and see if they are tractable. So they come in a bunch of flavors, but generally we can say that they are undirected or directed ones. Undirected are basically Markov networks. Markov networks are factorization of unnormalized probability distributions. So these factors, we might compute like complete evidence, but the issue is that, we need to compute also the partition function to normalize that. And this is intractable. This is, again, another kind of intractability related to the one from variational autoencoders. We have basically to sum or integrate over an exponentially large number of values. So also Markov networks are not that good for this kind of very basic and maybe probabilistic inference. So let's move to directed models like Bayesian networks. And Bayesian networks are still factorized models, but now they are normalized. We do not need to compute a partition function. And we can compute complete evidence in linear time with respect to the number of variables. So they're good. So let's stick to Bayesian network, at least for now. And let's move to the next class of queries we would like to answer. And we just saw this kind of query, marginal query. So basically, when I ask something like, what is the probability that today is a Monday and there is a traffic jam on Herzl Street? I'm not considering the time. I'm not considering all other Boolean variables for all the other streets. I'm marginalizing them out. So basically, and in the more general case, I have to integrate all the remaining variables out, or if they are discrete, I have to sum them out. These are marginals. And suppose I can do, in a tractable way, marginals, then I can also do conditional queries. Conditional queries would be, for instance, that given that today is a Monday, so in natural language it's slightly different, this would boil down to compute a ratio between the joint probability distribution of my query and my evidence variables and a marginal probability. This is why, if you can do marginals, you can also do conditional queries. So let's go back to our class of models. So we said, oh, it's cool, we can use Bayesian networks to answer conditional queries. Well, not really, because per se, marginal queries are hard. So to compute them exactly, we are in trouble because we are with a sharp p-complete problem. And even approximations, if we really want guarantees, are intractable. This is due to the fact that general algorithms for probabilistic graphical models look at the structure of the model. And the structure has this property called the tree width, which informally we can say it's like the way we can define our model to be similar to a tree. Slightly more formally, it's the minimum width of any possible tree decomposition of our model. We really don't need to get into details, but you can think about this. The more complex the model is, just the structure, all the black box inference algorithms for PGMs are going to basically have a hard time computing marginals. But things can get better if we just realize, by looking at people doing work on complexity theory, that in the worst case, for marginal and dense conditionals, we can compute those queries with time that is linear in the number of variables, and is like exponentially in the tree width. So a natural question is, what if we fix the tree width to a value we can manage? Let's say a small value, So that becomes a constant, and inference becomes just linear in the number of variables. This is a cool thing. And this inspired lots of research just by bounding the tree width of PGMs. So we can have trees by having just one parent, we're bounding the tree width, or we can have multiple parents but still requiring just one path between nodes. We can also just limit the number of random variables appearing in a clique in a junction tree, such that we have a thin junction tree. So now suppose you are limiting your tree width, and then you can have basically, let's say, by a value by 20. In practice, you can compute marginals and conditionals. So low tree width PGMs are somehow appealing to us. So let's peek into one of these models. Let's peek into trees because they are very popular and they have been used a lot in the community. So trees are just like Bayesian network with any nodes in that having a single parent. They still are like these factorizations. And the cool part about these kind of trees is that we can compute evidence, we can compute marginals and conditionals in time linear to the sides of our input. Moreover, we can also do learning exactly from data by the CHORU algorithm. We're going to exploit this later on in the learning section quite a lot. So we can have a trees, but we can also ask you right now, okay, we know that we are bounding the tree width. We are losing something, right? What we are losing exactly? We are losing the ability to express all possible probability distributions. So basically, suppose your data, your true distribution is not a tree. It's like a complete Bayesian network. If you limit yourself to learn a tree with a CHORU algorithm, you're never going to get that. You're never going to get the true distribution. You're going to lose something. So this is a price we might want to pay. But at a certain point, we might also want to exploit and go for other tricks to increase our expressiveness, to try to represent more complex distributions. How do we do that? One way to do that is with mixtures. So mixtures are another popular, old-fashioned, but very, very cool way to increase the expressiveness of a model. So look at this mixture of two Gaussians. Each Gaussian is like unimodal, but if we put them in a mixture together, we can model also a bimodal distribution. So we are getting something that is more expressive. We can increase this expressiveness, and still we can compute evidence, marginals, and conditionals linearly in the number of components of the mixture. So this is cool. This is a useful tool we're going to use lots of time later on. But another question we may want to ask is that what do we lose? Is it really true that we can basically represent anything, just increasing the number of components of a mixture? To answer that, before answering that, let's make another observation. A mixture model encodes a latent variable that basically tells you which component you are selecting from the mixture. This is like a very strong property of mixtures that will come handy later on, but it's also going to be one of the sources of inefficiency. So back to our question. So are mixtures that expressive? Well, it's known that a mixture of Gaussians is asymptotically able to represent with arbitrary accuracy any distribution. But that is asymptotically, and it means that we need a lot of components. And in practice, asymptotically, we are all dead. So it might not be the best thing to do. So let's switch definition and try from expressiveness to look at expressive efficiency, sometimes called also succinctness when we talk about Bayesian networks or we talk about circuits. So basically, we want to see if our distribution, the size of the distribution, is related to its expressiveness. Basically, it boils down to asking the question, how many components in a Gaussian I do need to fit a very complex distribution? So this is like a cartoon for you to get a feeling. On the left, you have a simple two-dimensional distributions that are somehow fancy, like concentric rings, a sinusoid, a funnel, and the banana distribution. I'm not saying that you're going to find them in real life, but you may want to fit your distribution over that. So you limit yourself to mixtures of Gaussians. How many Gaussian components do you need to fit very well these distributions? In every column, I'm increasing the number of components, and I'm also highlighting by these red ellipsoids which Gaussian components is fitting that region of the 2D space. So I'm just using, maybe this is working. In here, 2 components, 10 components, and the fit is pretty bad. I need 100 components to get something that resembles that. So we might say that asymptotically we can express any distribution, but it's not really expressive efficient. We need lots of components to be able to do that. So let's say that for now we stick to mixtures. This is like mixtures of simpler models, maybe mixtures of trees. That's the best model we have so far. And let's move to the next class of queries we might want to compute. MAP, maximum a posteriori, which also in the community sometimes is referred to MPE, the most probable explanation or evidence. One query of this kind can be answering this question. Which combination of road is most likely to be jammed on Monday at 9 a.m.? So to do this, we have to condition, but also we have to compute this argmax over the j, the possible indicator variables. So can we do that with a mixture? So this is the general formalization, but the moment we switch to the mixture, we have to recognize that we have to deal with the latent variable that the mixture implicitly encodes. And if we have to deal with the latent variable, whenever we have to compute the maximization problem, inside of that, we also have to solve before a summation problem. And unfortunately, we cannot swap that. So as we will see more in detail later on, whenever we have latent variables, we cannot compute maximum a posteriori queries exactly. So we have to get rid of mixture models or get something better. And you may think that MAP is a complicated query, but for this case, for latent variables, it's just like marginalizing and then computing the MAP solution, which as a query would be something like asking to yourself which combination of road is most likely to be jammed at 9 a.m., marginalizing over all possible days. This is a more general class of queries, which unfortunately it's very hard. It's NP to PP complete to compute. And the sad story is that it's NPR also for trees. And even sadder is that it's NPR even for naive-Bayes classifiers. So it seems like we are left with basic queries, probabilistic queries we would like to answer, and we do not have interesting models to answer that. But before getting into this kind of sadness, I just really wanted to push you and say that if we really want to do probabilistic reasoning, we want to do something more than just asking these toy queries, baby queries. So we would like to answer something more advanced. One example comes from the initial one we saw before, like it was computing marginals, performing map inference, and involving some form of logical reasoning. We can have something different, like involving comparisons between groups. Like, what is the probability of seeing more traffic jams in Jaffa than Marina? So we need to count, and we also need to compare between different sets of instantiations. This is also not so complicated from a natural language perspective. As a decision maker, you would like to question that and have an answer. But for our models, it's quite complicated. Later on, we're going to see that given some structural properties, you're going to be able to solve this kind of advanced queries. So for now, we are left with this kind of sadness. And yes, more involved queries coming later on. But there is one model is coming at our rescue, the full factorized model. If we assume that everything is independent and is super simple, we can answer all these kind of queries very easily. Why? Because we can solve all these kind of problems in parallel. And this is a form of divide and conquer strategy we would like to exploit later on by playing our cards well. So this is how the story told so far. We had a bunch of query families, and we saw a bunch of models. So let's try to wrap this up in a cartoon. Let's draw some axes. And on the x-axis, on the horizontal one, let's put this vague thing like, let's place all less expressive or less efficient models on the left, and models that are more expressive or more expressive efficient on the right. On the vertical axis, on the y-axis, let's try to put models that are more tractable, given some more query families, and models that are less tractable on the bottom. This doesn't really make sense. It's like an artist's impression of tractability versus expressiveness, but basically the higher on the y-axis the model is, let's say, the largest class of query family is able to compute. So the bottom line here is that we have a bunch of models that are very expressive, but they are not really tractable. And we have these marker networks, Bayesian networks, of course, GANs, and VAEs. We also have fancier versions of Bayesian networks like NATEs, MATEs, and autoregressive models. On the other hand, we saw some models that are tractable, but they are not so expressive. And these are all the bunch of bounded tree width model and other PGMs and also mixture models. They can do something. They are they are expressive, but not much expressive efficient. So we can put them there. So we would like to actually, if we have to pick some model or define our own framework, to be here. This is like the sweet spot we aim for. And this is what we're going to try to build in our framework with probabilistic circuit later on. So I'm giving back the word to you.
All right, so now that you're convinced that everything is very difficult and very intractable, my role will be to convince you that there's just a very small number of very simple ideas that make everything very tractable. So different vibe. So wake up again. So what are we going to do the next 15 minutes? I will try to go over the basic building blocks of tractable models. We're going to build something that looks like a computational graph, a circuit, a probabilistic circuit, which is going to do most of the work for us. And then we'll try to analyze which queries these probabilistic circuits are tractable for and what properties we need from them in order to answer all of these very complicated questions Antonio mentioned. And then afterwards, we'll again go into this alphabet soup and for all of the tractable probabilistic models, explain how they're really all kind of basically the same thing. They're all different flavors of this basic idea. Okay, what is the simplest tractable probabilistic models? Well, Antonio mentioned if everything is factorized, if all you have to look at is a single random variable, then things are easy. And so this is the base case of these probabilistic circuits. They're univariate distributions. So we have one random variable x, and we plug in some value for x. So it could be the value of a Gaussian or a Bernoulli, and out comes the probability or the probability density of that state. And so this is easy because we can compute the probability of evidence. That's just evaluating our Gaussian, let's say. We can also marginalize. We can integrate these one-dimensional distributions very easily. And we can also compute the mode of these distributions because, again, they're very simple. And so this will be the base case. Often it will be even simpler. So often when we deal with discrete data, these base cases will just say 100% probability for some variable, being, let's say the weather is sunny, 100% probability. And there will be some other base case that says the weather is rainy with 100% probability. So we'll only even look at these extreme univariate distributions that just assign all the probability to one value. So this is how it works. You plug in whatever the temperature, and out comes the probability density. Okay, let's try to be a bit more ambitious. Univariate distributions are not that exciting. So how do we combine them? Well, the simplest possible way to combine a bunch of distributions is by basically treating them as independent random variables. And that's what you see here. We have 3 random variables. We'll pretend that they're completely independent, fully factorized. And now we can define the joint distribution over these 3 variables as the product of the individual probabilities. And so we'll denote this by this product note here. And for example, if you have a multivariate Gaussian with a diagonal covariance matrix, this is basically what you're doing. Okay, you're just having these independent Gaussians that you're multiplying. How do you evaluate such a little probabilistic circuit? Well, here you have your univariate distributions. They say that all the variables that you're observing, that they have some probability, for instance, 0.8, 0.5, 0.9. And now the probability of them jointly taking those states is just the product of the 3, for instance, 0.36. Okay? So I'm not going to tell you any kind of rocket science. This is all just going to be very basic probability, but it's going to add up to something very powerful. Okay, so these were factorizations. Unfortunately, if we only factorize, then we again don't really have that much expressive power, because then everything always has to be independent from each other. And so the way around this is by taking this other idea of mixture models and applying it to these probabilistic circuits. So what we'll do is we'll build these basic computational units where we take two distributions, the two blue lines here, and just combine them with a weighted average into one distribution. Okay. This is what it looks like as a probabilistic circuit. So we have some simpler distributions over here, which could be two Gaussians, two different ones, over the variable x. And we'll take the weighted sum of them to get our new distribution over x, which could now be multimodal, right? So we have somehow gained expressive power. So again, the way that we evaluate these things is we get the probability of these components, and the probability of the mixture is just the weighted sum of the two. All right, so these are really all the basic building blocks that go into a probabilistic circuit. So we have the univariate distributions, we have the mixtures of distributions, we have also the product of distributions, which we can then combine with mixtures, and we can do this for many, many layers. We can create a deep tractable model, and we can also reuse some computation. So this is a directed acyclic graph, and the only thing it does is it combines all of these univariate distributions using sums and products. And that's it. There's nothing more to it. Okay, so what are these probabilistic circuits? Well, you might be tempted as someone who attends UAI to call them probabilistic graphical models. Well, they're definitely probabilistic, and they're also graphical models. But they really have a very different, they're definitely graphical, but they do have a very different flavor from your standard probabilistic graphical models. So in standard models, the nodes are random variables and the edges are dependencies between them. And then you have a bunch of inference algorithms that really in many different ways just take this declarative representation and compute probabilities for you. So in these probabilistic circuits, it's a little bit different. So the nodes are really units of computation, and the edges give you the order of the execution. And so you have a feed-forward pass often and a backward pass. And so the structure of your graphical model in some sense already tells you how to compute things. And so that's the key distinguishing factor, and that's why they're more like computational graphs, more like neural networks. Okay, so what are the benefits of this representation? Well, if you have a kind of generic directed acyclic graph, what you can do is you can reuse a bunch of computations. You can compute some little probabilistic circuit once, and then reuse it in many other places inside of your larger circuit. That means you can amortize inference, you can share certain parameters, you can share a lot of structure, and this is really what distinguishes it from probabilistic graphical models and why these things can be very efficient where probabilistic graphical models are not. They have this clear operational semantics, and by just looking at how to compute things, you can immediately tell how much it will cost you to compute things. You just look at how many sums and products you need to do. Things are differentiable. You can do gradient-based optimization. We'll talk about that later when we learn these circuits from data. And what's really nice about them is that you can now look at additional properties of the circuits to tell whether you can answer certain queries efficiently or not. Okay, well, it's actually a little bit more difficult than that. So up till now, I kind of pretended you can just arbitrarily nest sums and products, just like in a neural network, but there's a few extra things you have to ensure. There's some basic structural constraints that you need in order to be tractable. And so I'll quickly explain those. So what do we need to get from this circuit? How do we need to be careful when we construct it such that we can answer things efficiently? Well, there's, in some sense, the most important property of all, which goes back 20 years, which is the property of decomposability. And this is really the idea of independence in probability distributions, independence in graphical models applied to these probabilistic circuits. And so it is the idea that anytime you multiply a bunch of distributions, you have this multiplication node, all of the children, that they must talk about different sets of random variables. For example, here we talk about x1, x2, and x3. These are all different distributions, so you can just say, oh, we're assuming this independent product of these three distributions. Over here, we have a circuit that's not decomposable because we're multiplying a distribution over variable x1 with another distribution over variable x1. And of course, it doesn't make sense to say that x1 is independent of x1 and just multiply things. So this is not allowed. Okay. And then there's a second property that we need to ensure, which is called smoothness, also sometimes called completeness in part of the literature. And this property is saying that anytime you have this mixture of two distributions, let's say here we have a mixture of a distribution over x1 and another distribution over x1, then these distributions must range over the same random variables. And if you think about it, it makes sense, right? I cannot create a mixture model over the weather and which day of the week it is, because a mixture model always needs to mix two distributions that have exactly the same random variables in them. Otherwise, somehow here you're not accounting for the day of the week, and over here you're not accounting for the weather, right? So that doesn't make sense, and therefore we require this smoothness property. Mixtures only of distributions of the same random variables. If you don't have smoothness in your circuit, no stress, you can always make things smooth by adding a bunch of nodes here and there. All right, so these are the basic properties we would always need. And now suddenly things become tractable. Suddenly we can do tractable marginals, right? We can sum out random variables. We can do conditionals because we can do marginals. And so this is roughly how it works. If I have a distribution that is a product of two distributions, meaning I have this decomposability property, and I need to marginalize, meaning I have to integrate out x and y, then, well, p of xy becomes the product of p of x times p of y. And so now I can really just integrate p of x separately from p of y. Okay? So again, there's no rocket science here. This is just a very basic property of independence. Now, the nice thing is that because we have this computational graph, we can really just do this operation at every single product node in the entire circuit to simplify our marginalization task. Okay. By the way, feel free to ask questions anytime. There's a mic there. I see that people get more confused. Feel free to interrupt. Okay, marginalization by decomposability. So this tells you what to do if you have a product node. What if you have a sum node? If you have a sum node, then we have this smoothness property, which says that we really have this weighted sum of a bunch of other distributions, this mixture model. And now if I need to integrate some variables out of this distribution, then I can kind of rewrite it as integrating these variables out of the weighted sum of these different components. And then I can just change the order of the integration and the summation, and I can integrate in every component separately. And so this is the other trick that allows me to take this marginalization task and kind of start from the root of my circuit and push it all the way to the leaves of the circuit by just decomposing with decomposability and pushing these integrations into the summations. In the end, what you get is you get some integration problem that only talks about a single random variable, and that's always easy. And so then we're done, right? So now we have this recursive algorithm for marginalization on the circuits. Make sense? Okay. This is roughly how it works. Here we marginalize. So here we had a variable x1. And so x1 is one of the variables we want to marginalize out of the distribution. So that already tells us that this node here will just be 1. Because if we integrate out x from a distribution that only talks about x, the probability is going to be 1. Right? This is a normalized distribution. Over here we have some other number. This is the value for x2. So x2 is not a variable that we're marginalizing out. x2 has a state. For instance, x2 is set to true. And now this is the probability of this particular state. And you can do this for every single node, every single univariate leaf in your distribution. You either integrate it out, it becomes 1, or you replace it by the probability of the evidence, the thing you observe. And then the only thing you're left with is that you need to take sums and products. So now if you take sums and products, what you get is that the probability of the state that you plugged into the leaves is going to be 49%. So this is one forward pass, linear in the size of your circuit, and it computes the marginalization task. With 2 of them, you can do the conditioning task. Okay. So now we already have a tractable model that is quite powerful and can solve kind of the base case of, or the simplest query of marginalization, but we would like to do more. And if we want to do more, then we need some extra properties. And one of these extra properties is called determinism. So this is, again, a very basic property. It's sometimes called selectivity in part of the literature. And the idea is that anytime you take a mixture, instead of just an arbitrary mixture, you only allow for these sum nodes to mix between two distributions whose support is disjoint. So what does this mean? So over here we have a mixture of these two distributions, and I constructed this circuit such that the distribution here over x1 is only has a non-zero probability if x1 has a value less than theta. This is let's say some truncated Gaussian. Okay. Over here I have another distribution that says x1 only has a probability that is non-zero if it's greater than theta, another truncated Gaussian. Now I know that between these two distributions, if I plug in any value for x1, that at most one of these two guys will have a probability that is greater than 0, because again their supports are disjoint. And so that is a property that we require. Every sum node, every mixture is of these two distributions that are never really have any probability mass at the same time in any one possible world. Here's an example where you don't have determinism. So here we have a mixture of two distributions that are just arbitrary products of Gaussians over two variables x1 and x2. But now if I plug in a value for x1 and x2, then both of these distributions may have some density that is non-zero. And my mixture here may sum these two densities into some other value. And that's not allowed if you want determinism. Okay, why do we care about determinism? Well, determinism allows us to compute map inference efficiently. And so map is when Antonio talked about map, it was this disastrous query that nothing is tractable for. Well, with this property, you can compute things efficiently. So roughly the way it works is for these decomposable products that if you would like to find the map state, which is the most likely state of the world, well, instead of finding the state that talks about the x and the y variables, you can just first take the x variables, first part of your product, maximize those, and then separately maximize the state of the y variables because the x and the y variables are disjoint. We have a decomposable product here. Right, so anytime we have this factorization, we don't really need to optimize jointly the entire joint distribution. We can optimize the state of the two distributions separately. And that makes things much easier. Then for the sum nodes, we require determinism, and indeed determinism will be this trick that allows us to also solve this map problem. And so here's roughly how it works. So again, I need to find a state of these variables that maximizes the probability in this distribution. Now the issue is that we have a mixture. So now we're maximizing over the sum of these weighted components of my mixture. And in general, this is difficult. However, because of determinism, we know that for any world, for any solution we may possibly find, any value of any state of these variables, that really only one of the components will have a non-zero probability. So what does that mean? If in our solution only one component has a non-zero probability, then it doesn't make sense to sum up all of the probabilities of the components because you're just summing up one number with a bunch of zeros. Okay? And that allows us to basically maximize over all of these components instead of summing. And now we're maxing a max and things become easy, and we again just push the problem down into the circuit and we decompose it into pieces, smaller pieces. And then when we hit the leaves, then we have an easy problem.
Isn't that pushing the difficulty in the training? Because now you have to train over W's and theta, and you have to make sure that...
You mean training to ensure determinism?
No, training your network.
Mm-hmm.
Right now you have an extra parameter, your theta, that you didn't have before, and it's probably... Like
So,
when you're learning this network.
oh yeah, you can use the mic there. So the question is whether you have extra parameters theta. I don't see the theta show up here, but so the weights here are the only parameters that are added to our distribution here. Right, so anytime we have a mixture, we need to weigh the two mixture components. That is there no matter if you have a deterministic or a non-deterministic circuit, that weighted mixture is always there. So those parameters you will have to learn. And so Nico will talk about how to train those parameters. Yeah, I'm not sure if that answers your question. Okay, okay. All right. We can do tractable map. The way it works is we take those sum nodes, and because of determinism, I just told you, you can take the sum nodes and turn them into max. All you care about is maximizing things. So now you plug into the leaves the probability of your current observations. For instance, it's a Monday today. And then for all of the other leaves, you just set them to the mode of your distribution. And for example, here, x1 may have some mode. This x1 is also a distribution over the same random variable. It may have another mode. But we instantiate everything to its mode because we're trying to find the most likely world. And then the only thing left to do is multiply max, and we get at our output the probability of the most likely world. If you don't care about the probability, but you would actually like to know what is that world, then that's also easy. You have to do a downward pass, and you have to figure out, well, the max here really chose this number over this number, because it found that in the mixture, this mixture component didn't have as high of a probability state as this one here, so it went and picked this number. You do this recursively, and now you can decode the state of all of your univariate distributions that made up this solution of your map query. Okay, so a little bit of hand waving, but it's all very efficient, it's all linear, it's all quite nice. All right. So what do you do if you don't have determinism? And a lot of the representations that people use in the literature, they're actually non-deterministic. You have these latent variables that are mixing between two distributions that may have support that overlaps, right? And so now the issue is that this maximization problem where you sum out this latent variable that is telling you which of your mixture components to choose, this becomes intractable. So what do people do in practice? They still pretend like this summation is a maximization. They add the latent variables to the distribution, and now they start to maximize also the state of the latent variables. And so this is something you can do, and it's often a useful approximation of map when you cannot get the exact value. So you will often see this done in practice. Okay. Okay, let's add more properties. So now we had decomposability, smoothness, and determinism. Next property is called structured decomposability. And structured decomposability is going to be a pretty amazing property because I will soon show you a slide with like 15 different queries that suddenly become tractable just because of this one property here. So what is the property? Well, in general, anytime we have these products, they have to be decomposable, but they don't always have to be decomposable in the same way, meaning that they can split the set of variables any way they want. They can partition the set of variables any way they want, as long as there's no overlap, but the different products may choose to do so in different ways. Now, structured decomposability is saying that anytime you have a product node at the first level here, it always has to create a factorization, a multiplication between a distribution over x1 with a joint distribution over between x3 and a joint distribution between x1 and x2. So all of these nodes, they all have to go x1 and then the rest, x1 and the rest. You cannot kind of do things in other ways. Similarly, anytime at the second level you have decomposability, it always has to be in exactly this way. This is kind of the bottom layer, so there's no other way to do it, but that's the general principle. So this is a decomposable, structured decomposable circuit. Here's a circuit that is not structured decomposable, right? And the reason why is that this node here does agree with the fact that it must split x3 from the rest. That's what it does here. It has a distribution of x3 and the rest. However, this product node is still decomposable, but it splits differently. It splits off x2 versus x3 and x1. So this is not structured decomposable. Okay? Now, for reasons that I don't have time to get into in 2 hours, if you have this property, you can build a lot of really nice, elegant, recursive algorithms that reason about the structure of your circuits. And these things are incredibly well behaved. And what you can do is all of this stuff. If you have a probabilistic circuit that is decomposable, deterministic smooth, and furthermore structured decomposable, you can efficiently compute the entropy of that distribution, of that probabilistic circuit. You can ask a whole bunch of these difficult queries that Antonio mentioned. You can ask, what's the probability that exactly 25 roads in Tel Aviv are jammed? That an odd number of them are jammed? That more roads are jammed in one district versus the other? All of these types of queries, which are extremely difficult, become tractable. This is for any V-tree, for any way that you choose to do this structured decomposability. Now, if you pick the right way of decomposing, if you kind of enforce how this V-tree looks, then you can do even more. You can compute the probability of any kind of logical event in the probabilistic circuits. You can multiply two probabilistic circuits in quadratic time. You can compute the Kullback-Leibler divergence between two probabilistic circuits that have the same V-tree. These are all things that, to UAI people should sound like insanely intractable, but you can do all of this exactly with these tractable probabilistic models. There's a bunch more papers that have been written about various queries I won't get into, about decision making, about active sensing, about how to decide which features to prune, feature selection on a distribution, how to compute expected predictions of a classifier with respect to a distribution, how to do even marginal map. Okay? So this is just to tell you that nice properties give you nice tractable behavior. Okay? All right. So for the next 10 minutes, you can wake up again. We have this language of tractable models, and we'd like to very quickly describe how they relate to other types of representations you may have seen before. For example, logical circuits. For example, SPNs, arithmetic circuits, and so on. And also how they relate to these low tree with probabilistic graphical models that we talked about earlier. And so the goal here will be to convince you that they're all just different syntactic variations on this one simple language with these simple properties. Afterwards, we'll talk about how to get these circuits from data. And that will be Nico's part of the presentation. Okay. Nothing I told you so far really depends on the fact that you're dealing with probabilities. I was just taking sums of products. And so that means that I can do sums of products in different ways, in different semi-rings. And that's essentially what happens if you take these circuits and turn them into logical circuits. So what you'll do is you take the sums and you turn them into disjunctions, or gates. You take the products and you turn them into conjunctions, ands. And now you have a tractable language for logical problems, not probabilistic problems. And so these things have existed for many, many decades. So here's a bunch of them. There's what's called structured decomposable negation normal form circuits. These are very popular in logical reasoning. There's OBDDs, which are even older, binary decision diagrams. So these, at some point, this paper was, I think, the most cited paper in all of computer science about 10 years ago. So this is really the workhorse of a lot of formal methods verification, logical reasoning in computer science. Sentential decision diagrams are another kind of recent addition to this. And so these are really the same as these probabilistic circuits, only they don't have probabilities. They do have all of the same properties of decomposability, determinism, smoothness. And in fact, this is the origin story of tractable probabilistic models, is these logical representations where we just sprinkle some probabilities over them, and now we get a tractable probabilistic model. Depending on which properties, you again get tractability. For example, if you have a logical sentence that is decomposable, then I can solve the SAT problem in linear time. And normally SAT solving is NP complete, right? So I can give another presentation just about logical reasoning where I tell you exactly the same story with different types of queries. How does this connect? Well, the way that people went from logical circuits to probabilistic circuits is through this notion of weighted model counting. So weighted model counting has been used for about 20 years to do probabilistic reasoning in the UAI community. And in fact, I think in all of the most recent UAI inference competitions, this approach was basically winning half of the competition. I think FIBAF solvers were winning the other half. So this is the general idea is you take your probabilistic model and you somehow encode it into logic. And the way that you encode it into logic is that you take all of its parameters, all of the numbers in your conditional probability tables, and you introduce a new variable for them that is a logical variable. And that logical variable will somehow kind of represent as a placeholder the fact that this parameter applies to a particular possible world. That it will be multiplied into the probability of a possible world. And then weighted model accounting is just saying generate all of the possible worlds. This is kind of like summing over, this is like marginalization. And this product here is looking at all of the variables in some sense, all of the variables in your logical formula that have to be true, meaning that these are all of the parameters that you need to multiply to get the probability of your possible world. And again, this is a lot of hand waving because I don't have time, but this formula allows you to bridge between logical reasoning and probabilistic reasoning. And so the general framework is you take your Bayesian network, let's say, turn it into this weighted model counting problem, which has a logical part and a bunch of numbers that you associate with these parameters. You compile this into a tractable circuit. Once you have this tractable circuit, you evaluate it, and in linear time, you get the probability of your marginalization task. And depending on how you do this, you may even be solving the MAP problem. Now, the big takeaway message here is if you take this pipeline to probabilistic reasoning, it's really equivalent to building a probabilistic circuit. It is nicer for people who like logical notation, but otherwise it's exactly the same thing. All you need to do to translate from one to the other is to take your logical circuits, for example, this one, and now you replace your ORs by sums, your ANDs by products, and now you take all of those parameters and you sprinkle them on the edges of your graph, and you have exactly the same probability distribution. Okay, so this is a 1-minute version of how to connect logic and probabilistic circuits. Unfortunately, I cannot go into more detail. All right, what's another connection? So we talked earlier about these tractable models that had low tree width, that were very sparse and therefore tractable. Well, it turns out that these tractable models, they have a very simple, efficient translation into a probabilistic circuit with all the right properties. And let me try to quickly convince you of this. So here we have a Chow-Lu tree, a tree-shaped Bayesian network that is efficient. It is tractable. And we can turn it into this probabilistic circuit here. And the way to do it is with a simple dynamic programming algorithm. So let's start at the bottom of the Bayesian network with this distribution here over the variable A. So this distribution we would like to turn into a very simple probabilistic circuit. And this is what it looks like. So we will have to assume something about the parent of A, which is C. So let's assume that C is set to false. Now I just have the distribution over A given that C is set to false. And either it is 0.3 probability if A is false, or it's 0.7 probability if A is set to true. Okay. So what I get here is I have my mixture of my two components. This is deterministic. You cannot simultaneously have that A is true and false. And the leaves here are univariate distributions that say 100% probability for A is false, 100% probability for A is true. Okay, very simple little gadget. I can do exactly the same thing, now assuming that the parent is set to true, and I get another distribution over A. I do the same exercise for B, and I again get this. Now I have 4 little probabilistic circuits. And now I have to connect all of them because they all have this parent, C. So what do? I have to instantiate, I have to build a distribution for the variables A, B, and C, but that distribution must depend on the value of D. So let's just first assume that D is set to false. Okay? If D is set to false, then with 0.2 probability, I have this distribution here. This distribution says that C is false, and then here we connect these two distributions over A and B, where we assumed C to be false. With 80% probability, we will assume that C is set to true, and then we have to multiply with the probability of A and B, given that C is set to true. All right. Again, I do the same thing, but for when D is set to true. And then finally, I compile this last little node in my Bayesian network, and I say D is set to false with 50% probability, and it's set to true with 50% probability. And I hope you're convinced that by just going through this very simple Bayesian network from the leaves to the root, you can compile this circuit, and the circuit is just linear in the size of the Bayesian network. So what's the takeaway message? If you have a low tree width probabilistic graphical model, then we can efficiently turn it into a probabilistic circuit. Moreover, that probabilistic circuit is going to be decomposable. Everything I showed you on the previous slide was decomposable. It's going to be smooth and it's going to be deterministic. This tells us that on low tree width probabilistic graphical models, we can compute the probability of evidence, marginals, conditionals, and the map state all efficiently. We can build special algorithms for doing these types of queries, or we can just say, turn it into a probabilistic circuit, and now we know how to solve all of these things. Okay? Question?
The number of states matters, right? So you always had like binary, D is binary, but if you have more states, it scales up.
Yeah. So the question is, how does it depend on the number of values of the random variables? So it will also be linear in that. So it's going to be number of variables times the number of values of those variables.
But multiplied for every, right? So D, the number of states, times the number of states to C, times...
Yeah, so the number of nodes we will have to introduce for D will just be one for each value. So for false, for true, for rainy, sunny, snowy, whatever. Right? But all of this is still polynomial. It's still efficient to do. Okay, good question. All right, so low tree width PGMs are just probabilistic circuits. You may have heard of arithmetic circuits, and arithmetic circuits kind of come from this logical circuit community where people compile logical circuits and then kind of turn them into arithmetic circuits. And these are also probabilistic circuits. They're also decomposable, smooth, and deterministic, so they all support the same things. All of these queries are, again, tractable. The syntax is slightly different. The only difference is that in these arithmetic circuits, the parameters are not associated with these mixtures in the sum nodes. They're actually inputs to the circuit in their own right. But it turns out that this is not important, and you can just translate from one to the other. Right? So this is just a bunch of syntax, but nothing to worry about. Some product networks are also very well known. They're also a type of probabilistic circuit, and they look exactly syntactically like the ones we had before. Now, the only difference is that these are assumed to be not deterministic. So they are decomposable and smooth, but in general, they're not deterministic. If they are, then they're sometimes called selective sum product networks. And so what that means is that because they're not deterministic, you cannot solve map inference efficiently. And then cut set networks, right? So this is the whole alphabet soup that we're quickly going through. I promise you it will be over soon. Cut set networks are, again, a tractable probabilistic models. It looks like this. So here we have a decision node, and it's basically saying if x is set to true, then here we have a distribution over all of the other variables. If x is set to false, here we have another distribution over the same variables. So it's kind of a mixture, but it's a mixture based on the value of x. At some point, you just give up introducing all of these splits here, and you are left with a Chow-Lu tree, a tree-shaped Bayesian network. So it turns out these cut set networks are very easy to learn and very efficient, so we'll talk about that later. But as a representation, they're really just the same as one of these probabilistic circuits. Because you can just translate this little gadget here where you say, if x is true, then this distribution, otherwise this one. You can turn it into this little gadget where you just take it a sum that is weighted of a product of a variable that says whether x is false and x is true with the distribution you would like to get based on those values. So again, we have a different syntax, which is nice if you want to do learning, but as a tractable probabilistic model, this is a probabilistic circuit. It has the same nice properties, though, of decomposable, smooth, deterministic, so it is tractable in all these ways. And then finally, a probabilistic sentential decision diagram is also one that is kind of inspired by logical circuits with parameters to make them probabilistic. And they often have this extra property that they are structured decomposable. And as I told you, this extra structuredness gives you the ability to do all of these crazy complex queries like compute KL divergence between two circuits. Okay, so big summary. Where are these probabilistic circuits? Well, we have a bunch of them. They are all different syntactic variations, but they're all probabilistic circuits that are either decomposable, deterministic, or smooth, or structured. And I would like to convince you that, well, I think it's pretty clear that they're very, very tractable. I would also like to convince you that they're very expressive. And the way that I'd like to convince you is by, the proof is in the pudding. So I will show you a bunch of standard benchmarks where we compare Bayesian networks using a very nice Bayesian network structure learning library that learns nice context-specific conditional probability distributions. We'll also compare to what is, in some sense, the deep learning version of Bayesian networks, these autoregressive models that have all sorts of fancy deep learning tricks to learn the conditional probability distributions, but otherwise kind of looks like a Bayesian network. So these are very cool things. And we'll also compare to variational autoencoders. And so this is the overview for these standard benchmarks. And what you can see here is that these probabilistic circuits, when you learn them from data, very often they end up getting the state-of-the-art likelihoods. They end up best fitting the data, meaning that they are in fact expressive enough to model all of these distributions in ways that is sometimes better than Bayesian networks and better than autoregressive models, better than VAEs, despite the fact that they are so much more tractable. Okay? Of course, on some benchmarks, Bayesian networks do well, autoregressive models do well, or VAEs do well. But the big difference is that these circuits here, that they are in fact tractable. All right, I think we probably need a 5-minute break now. And after the 5-minute break is the machine learning part, how to get these circuits from data, and also some applications. So let's start again in 5 minutes.
Okay, we can say that a learner is tractable for a class of queries if for any dataset the learner runs in a polynomial time in the size of the samples in the data. And it gives out a probabilistic model that is tractable for the query sets. In particular, the model have a size polynomially in both the samples in the data and the number of variables. And the efficiency of the inference is polynomial in the size of the number of variables. So here we will to see how, given a training set, how to learn both the parameters of a given circuit structure, or how to learn both the structure and the parameters in a single step. As we already said, some nodes in a circuit have a latent variable interpretation. In particular, some node represents a marginal distribution over a set of random variables and another hidden variable. And in particular, the conditional probability is the child distribution, while the marginalized probability on the hidden variable represents the weights. Furthermore, in the case of continuous data, the leaf distribution may be modeled from, for example, with a Gaussian distribution, and hence we require to learn the parameters of the weights of the sum nodes and the parameters in the leaf nodes. So learning parameters involves learning both the weights of some nodes and some parameters involved in the leaf distribution. Okay, we have two cases. In the simple case of the deterministic circuits, learning parameters is very fast and simple, like in a Bayesian network. While for non-deterministic circuits, we have to use algorithms like gradient descent or expectation maximization. So given a fixed structure and a data set, the aim is to maximize the likelihood of the parameter with respect to the given sample data. So we have to find the maximum likelihood parameters, and this can be obtained by maximizing the likelihood. And it can be proved that in the case of the deterministic circuits, the maximum likelihood estimation as a closed form solution. So it's like for Bayesian network. We can compute parameters by just computing, counting sufficient statistics with a single pass of the training data. In the more complicated case where we have not determinism, one approach is to use gradient descent by considering a circuit like a deep computational graph, and then we can compute, like in neural networks, the likelihood gradient optimized with a stochastic gradient descent. We have two possibilities. We can optimize the parameters using a soft approach, or another approach where the difference is to use the derivatives of the sum nodes, or just counting some activations in the sum nodes. We can also use another approach based on expectation maximization by exploiting the latent variable interpretation of the sum nodes in a circuit. And since each sum node is a marginalization of a hidden variable, we can compute we can learn the weights by just computing the posterior of the hidden variables with respect to the weights. Other approaches are based on Bayesian learning, and in this case we have to impose a prior on the set of weights of all the sum nodes, and hence the learning corresponds to compute the posterior based on the training sets. However, this posterior for the case of circuits is intractable. Indeed, if we consider a locally normalized sum node, in particular a sum node where the weights sum up to 1, we can impose a prior on each sum node corresponding to a Dirichlet distribution. Hence, the whole prior on the set of parameters is a product of Dirichlet distributions. And so the posterior, in this case, becomes a mixture of products of Dirichlet distribution. And then the number of mixture components becomes exponential in the number of sum nodes. So we have to use different approaches to approximate this posterior. One approach is to use the classical moment matching approach in order to approximate the posterior after each update with a tractable distribution matching, for instance, the first and the second moment of the untractable posterior. So the joint prior can be approximated with a product of Dirichlet distribution, and the method is to use the first and the second moment of a tractable distribution in order to set the hyperparameters of the single Dirichlet distribution for each sum node. This moment matching approach can be also extended to continuous input variables, or the approximation of the untractable posterior could be used with a collapsed variational inference algorithm that has been proved to outperform the moment matching based approach. The last approaches to learn the parameters of a circuit are based on a signomial program. In particular, it can be proved that any complete and decomposable circuit is equivalent to a mixture of tree, where each tree corresponds to a product of univariate distribution. With this assumption, it's possible to prove that learning the parameter based on the maximum likelihood expectation principle can be formulated as a signomial program, and hence we can provide a sequential monomial approximation procedure in order to learn the weight of the mixture. Furthermore, it can be proven that this signomial program can be equivalently transformed into a difference of two convex functions, leading to another better algorithm based on the concave convex procedure. So when we have a set of data, but we have not a given circuit structure, we have to learn both the structure and the parameters. And this can be obtained by some greedy approaches or approaches guided by some heuristics exploring the space of possible circuit structures. Or furthermore, we can employ some randomized structural learning approach. The first principled algorithm to learn a circuit in the form of a sum product network is LearnSPN, that has inputs a data matrix of samples by variables, and it tries to decompose this matrix in order to find sum and product nodes. In particular, if the algorithm is able to cluster the instances, it discovered a mixture, and so it can model this mixture with a sum node. In a submatrix, if the algorithm is able to decompose the variables into independent components, it discovered a product nodes. It can be applied in a recursive manner in order to learn deep and deeper sum product networks by just relying on clustering rows and variables. This basic algorithm can be extended in different ways by leading to some variants, or as we can see, the structure can be learned using different learning principle. An interesting variant is IDSPN that works like LearnSPN by clustering rows or splitting variables. The key idea of IDSPN is try to model the leaf nodes with a multivariate tractable distribution using a tractable Markov network. Instead of model the leaf distribution with a univariate variable, it tried to model the leaf with an arithmetic circuits modeling a tractable Markov network. In particular, it starts the process by learning a single Markov network on all the variables, and then it tried to decompose these tractable networks into a sum of product circuits, following the same principle of LearnSPN. So at the end, we have a SPN with tractable multivariate distribution in the form of Markov networks. Other variants are learning in a bottom-up fashion. We can start with simple models or small variable scope, and then we can use, for instance, a maximum mutual information principle in order to aggregate a smaller scope in a bigger one. Or we can use an Hill-Klimbing approach in order to explore the neighborhood of a given structure by using some split or merge operations. Another approach is based on SVD decomposition. In particular, we can try to find an approximate rank 1 submatrix of the data, and in this case we have discovered a decomposition of rows and variables in a single step. Another variant of the basic algorithm has been proposed in order to learn deeper network by limiting the node splits. The regularization has been introduced using tractable multivariate distribution like for IDSPN. and the model is made robust by using a banking approach. Two other algorithms have been proposed in order to learn graph-based SPN by using some merging operations working on a tree structured SPN, or by using some graph partitioning procedure. Okay, a deterministic circuit can be learned with a very efficient algorithm. For instance, a cat-set network that is an OR tree that tries to decompose dependencies on the variables and then models the remaining variables with a tractable multivariate distribution, can be learned in a very fast way by using the likelihood decomposition. And the regularization can be obtained by using the Bayesian information criteria imposed on the learned structure. So as for IDSPN, the process can be started with a single multivariate distribution and then try to incrementally split this multivariate distribution into an improving cat-set network. Okay, probabilistic sentential diagram, as we already said, are an interesting arithmetic circuit that provides exact maximum a posteriori inference. And due to determinism, we can learn the parameters in a very efficient way. In order to learn a PSDD, we have to learn a variable tree. In particular, a variable tree is a binary tree where leaves are labeled with variables, and internal nodes of a tree try to split variables into independent components. The variable tree can be learned from data by exploiting statistics like mutual information. However, since mutual information among large set of variables is intractable, a possibility is to use an average pairwise mutual information in order to learn in a top-down or a bottom-up fashion the structure of a tree. Okay, given a tree, the structure of the circuit may be learned by exploring the search space using two operations, a split or a clone operation. In this way, the algorithm can incrementally change the initial structure of the circuits by exploring the neighborhood of that point. And in every step, the structure is changed, and the algorithm go in the most improving neighbor with respect to the best likelihood improvement per size increment. Logistic circuits may be used to solve some classification tasks. In particular, a complete assignment propagates the values and parameters in a bottom-up fashion. And at the root node, there is a weight that is combined in a logistic function. So, due to the decomposability of the logistic circuit and the determinism, it can be proved that any logistic circuit can be modeled or reduced to a logistic regression model. and that the cross-entropy loss of a logistic circuit have a closed form, and hence we can use any convex optimization algorithm to learn its parameters. The structure of a logistic circuits can be learned with an approach similar to learning synthetic decision diagram by using some split operation. Okay, the structure can be learned using also a Bayesian and non-parametric approach by defining a prior node by node. In particular, the prior for each subnode is a Dirichlet process, having a base distribution that is defined over the set of possible product nodes with the same scope of the parent subnode. So in this way, the prior distribution of SPN is specified with a tree of Dirichlet processes. And the model can be extended to graph SPN by using a hierarchical Dirichlet process. Another work aimed to overcome the problem in density estimator of assuming heterogeneous variable and shallow dependency structures. In particular, the proposed algorithm uses some product networks in order to capture the statistical dependencies in the heterogeneous data. And the algorithm is able to do inference for both statistical data type and likelihood models, is robust to missing values, is able to detect anomaly data, and is able to automatically discover the statistical dependencies and correlations in the data. In particular, here we sketched the generative model where we have to learn the weights of the mixtures of the subnodes. We have to learn the weights in order to select what distribution we have to choose the model to model the leaf distribution. Okay, another Bayesian approach to learn both the structure and the parameters of an SPN is another Bayesian approach that solve the problem of structural learning into two steps. The first step is to propose a computational graph that provides the arrangements of sums, product, and leaf distribution. And the second step is to learn the scope function that we have to assign to each subnode in the network. So the generative model is similar to the previous one. We have to learn the weights of the subnodes. We have to learn a parametric form for each leaf node. And furthermore, we have to learn how to attach the scope to each subnode in the model. There have been proposed also some discriminative learning approaches that have been taken by use the gradient descent, or with an algorithm that is able to learn the structure of a discriminative model by extracting features that are maximally correlated to the label, or with an algorithm that is based on moment matching as for the structural learning of a generative model. Okay, circuits may be learned also in a random approach. A way to learn a random SPN is to firstly construct a random region graph, and then to populate this region graph with tensors of SPN nodes. And in this paper, the authors propose also an interesting dropout heuristics in order to deal with overfitting of the model, and the obtained random SPN are comparable to deep neural network. At the same time, are probabilistic models that are able to model a complete joint distribution over variables. In particular, the approach is to maximize an objective function that is a linear combination of a cross-entropy loss and a negative log likelihood loss. In particular, if we set the lambda parameter to 1, we are optimizing a discriminative learning approach. On the other side, we are optimizing a generative model. In order to deal with the scarce accuracy of a single model, circuits may be used as component of a large mixed model. And in this case, the classical expectation maximization algorithm may be used. However, it is impractical due to problems about convergence and instability. So a solution could be to use a Bayesian approach that is more efficient than expectation maximization, where we set the mixture coefficient as equally probable. And the components of the mixture can be learned independently and on different bootstraps of the data. Another approach to learn deterministic circuits is to use a random subspace projection. Also, boosting may be used to learn circuits. In the simplest case, we can use a boosting density estimation that sequentially grow the ensemble, adding a weak base learner at each stage. The algorithm may be extended using a kernel-based generalization, but the best performing approach for boosting probabilistic circuits is to use a sequential expectation maximization approach, where at each step it jointly optimizes both the combining parameter and the base weak model to integrate into the boosting model. Okay, even a cut-set network may be learned in a completely random way. In particular, we have already said that a cut-set network is an OR decision tree with tractable leaf distribution. We can learn the OR decomposition tree in a completely random way, like in extreme tree. And these give us the possibility to learn mixtures of thousands of deterministic circuits. Okay, other approaches for learning circuits are based on incremental learning. There are two approaches, one for discrete data, that is a variant of the classical learn SPN approach, where the clustering algorithm is an incremental version of the clustering approach. And on continuous data, the idea is to start with a network, assuming all the variables independent, and then in an incremental way, we introduce the correlation among variables in the form of a mixture of a multivariate Gaussian. Okay. Two other slides on how to combine tractable models with intractable ones. Okay, in case of many variables, the circuits that we obtain can be exponentially sized. And hence, in this case, we could try to use a form of approximate inference. And a way is to use an online collapsed importance sampling, or another approach is to use a collapsed compilation approach. In particular, we want to maintain a partially compiled circuits during an online collapsed sampling. Another model is to combine probabilistic graphical models with sum product networks, in particular providing a sum product graphical model that always enable tractable inference by exploiting properties of circuits, and on the other side it provides also a high-level model interpretation, being a graphical model. Finally, another hybridization is to combine product networks with variational autoencoder that is a very flexible model, but it does not scale when we have a large set of variables. So the idea is to use a first decomposition of the variables using an SPN, and then try to learn many variational autoencoders on many subsets of those variables. Okay, we can see some applications of the model.
Thank you, Nico. So for the last part of this tutorial, my objective is to bomb you with additional references and very quickly, like in a clockwork orange style. So be prepared. So let's start with additional green to wake you up. And just a bunch of applications to show what probabilistic circuits have been used for so far in different flavors and why you should use them likely. And what are the current trends and also the current challenges which will turn into opportunities for the community? And straightly go into the conclusions. So let's start by density estimation, which is clearly one of the most used settings circuits have been used for. And you generally compute just the test log likelihoods on a set of standard benchmarks. And these benchmarks are the same we showed before. So you could say that we have a standard set of data sets and this should be a good thing. But truth to be told, these data sets are very simplistic and they are also quite poor in quality. So the first challenge as a community, if we want to do tractable learning or just probabilistic modeling, should be to move away from these toy benchmarks and try to get something that more closely resembles the real world. And the real world is complex and is heterogeneous in nature, and also contains lots of samples and random variables. So this is one thing that as a community we should actually try to pursue. But let's get into more applications, and of course there is like computer vision. And one task which is very interesting is like image reconstruction or in painting. And basically this boils down to map inference. When you observe a portion of an image, you want to predict what's the most probable part for the pixels that you are not observing. This was actually in one of the first papers of some product networks and somehow dictated the whole hype about these models. But it's also true that we are somehow stuck in this. And even though the circuits are somehow expressive, we still are trying to pursue the very fancy results that we are getting from all the other models like GANs and maybe also VAEs. But truth to be told again, all those models are limited in the set of pixels they can predict. So this set is generally fixed or follows some orders. With probabilistic circuits, we can have like any arbitrary set. And this is like the strength of math inference, even though we have to approximate it. And we can do this in a different flavors, being still in computer vision. We can tackle different tasks like image segmentation, semantic segmentation, and scene understanding, where the task here is to detect the objects and to try to remove them from a background and maybe track them. And this is another super cool paper that tries to combine now a tractable model as a small block inside a larger intractable model. And the striking results are shown on the right. And as you can see, probably you cannot tell because it's too small, but the story is that if you make inference tractable for even a small portion of an intractable model, you gain a lot. And you gain a lot also in data efficiency, and during learning, you know where to go, you know where to optimize. And by doing this, by placing like some product networks inside a larger intractable model, you can beat the classical attend infer repeat model, which is quite popular for scene understanding. So here is like the second challenge, which is also been previewed by Nico before. So we should also aim at navigate the spectrum of tractability and trying to hybridize tractable model with intractable ones whenever it's possible, and trying to get the best from both worlds. Getting more on other computer vision related tasks, we have activity recognition, may it be from still images or from videos. And again, we're just exploiting the properties we've seen so far from circuits. We can do map inference, we can decompose complex and tough problem into smaller problems. And we can also try to make a probabilistic inference and use that to make explanations, which might help providing like a sensible classification and communicate those to users and so on and so forth. Map inference can be used again in the domain of audio when we want to reconstruct speech and we want to extend bandwidth. So nothing really different from what we've seen so far. We can extend this to sequence labeling, and again, we have the structures provided by probabilistic circuits. We are putting on now sequential data, and maybe we want to have a language model. We want to predict like the next token given the previous ones. And this is yet another flavor of map inference. We can also go into the domain of the robotics when we want to do some planning or we want to understand the scene or the surroundings. And again, this is a complex problem. How do we tackle that? We decompose that into smaller ones. So we use a tractable model, in this case a probabilistic circuit, to decompose the problem at different levels. More interestingly, we can move into those more complex queries involving some form of logical reasoning. In this case, it's preference learning. So we can model some preferences or rankings as logical constraints, and therefore we can also build probabilities, distributions over them, and we can reason above them. So this is another very cool application that is enabled at the moment when we take into consideration structured decomposable circuits. Moving along this line and having some references floating in the air across images and not text, it's trying to to predict this time paths in a graph. So you can have, again, a decomposable structure by having a more complex map that boils down to connection into intermediate maps, which by themselves are like the composition of a smaller maps. Again, another form of decomposability that can be encoded in a probabilistic circuit. Now we have like our challenge number 3, trying to scale these models to really ImageNet size or even larger data sets. This is still an issue, and this is an issue when we want to learn them. So we are somehow limited, not by the data, but by this kind of algorithms that Nico shows so far. Because most of the time we are trying to also look for independencies, and this is maybe costly. So this is another challenge for the community. Lastly, we can go for trying to exploit circuits in whichever flavor they can, maybe logical, maybe probabilistic, for probabilistic programming. And probabilistic programming is becoming the de facto lingua franca of probabilistic modeling. So this is a very nice combination, which you can think of about like trying to bring circuits to the what was before like PGMs. Now it's like probabilistic programming languages. We can have like a bunch of application coming from the most varied domains, but let's not focus on them. And let's try to push for maybe what's really needed in the community, which is move away from these toy queries we are sticking with, which is complete evidence, the most trivial case, but also MAP. MAP is tough, is inherently tough, but we can do much better. We can aim at something much bigger, trying to automate reasoning in all these kind of subtle aspects that involve like some form of reasoning by considering logical constraints. So here are our takeaway for this 2-hour-long tutorial. So the first one is that tractability is a spectrum. It's defined by classes of models and is defined by classes of queries. This cartoon, this artist's depiction, may be the message you can bring home. You can reuse that also for the second takeaway, which is, yeah, sometimes you can be both tractable and expressive. There is this inherent trade-off. You have to come up to compromise, but you can get also very good models that are expressive efficient, and allow for a very wide range of queries to be tractable. It is good, but as we said, it's maybe not enough. We are putting under this umbrella name of probabilistic circuits like this framework, which has been tackled for many years from different perspectives, but this really brings like a foundation for tractable inference and learning. And we hope that the UI community might be more and more interested in these kind of models. So this is like the last slide, the fourth takeaway message. There is still lots to do. And these are the challenges I just briefly mentioned before. We need more benchmarks. We need more rigorous empirical settings to test our models. And these test bed settings have to be challenging. We need to scale our tractable learning to real-world scenarios and to real-world data. We have to take the best from approximate reasoning, if it's possible. If this means like hybridizing with intractable models, we can do that. And we can find a way that makes that, provides also guarantees. And let's move toward really more complex reasoning, more interesting queries. Yeah. I think that's it. And we have something like lots of pages of references we didn't check by ourselves, but you can do because the slides are somewhere online. So thanks to Guy, thanks to Nico, thanks to Vibab and Ryan for inviting.